This video is just for the first 2 pages of this packet on conceptual questions for Unit 3. So looking at number 1, right, just to make sure you understand that forces always move away from the object. So on part A, where you were pulling, and part C, where you were pushing, they look identical because the force should always move away from the object, not go towards the object. Some people would have a tendency on C to put something like that, but that's not what you're supposed to do. It's always supposed to leave the object. So for part B, because it's twice the force, that's why the arrow looks twice as long and it's going to the left instead of going to the right. For number 2 and 3, I think this was a little bit different for people, so people were a little confused. We would normally take this force diagram here and we would separate any diagonal forces into x and y components. So we could take this force and we could say that it has a y component and an x component. Oops. So when I'm looking at it, to me, these forces here look like they're identical, so they would cancel out. So essentially we know the sum of the forces in the y direction are 0, leaving only the x force left over. Well, if we want to draw the net force, right, one arrow that represents that net force, then the net force is to the right, and therefore that's why I only in my diagram here have one force going to the right and labeled that the net force. So looking at, let me erase this. Looking at number, or I guess part B for number 2, right? If you're looking at these forces, we have something moving to the side, another one moving to the side, and it appears that this force here is a little bit longer, and that's why I made my net force to the left. On number 3, if we separate it into the y and the x, again, to me, it looks like these x forces cancel each other out, which is why I have a net force that's, right, only down. And on number 3, part B, that one's a little bit harder. If I'm taking this one, if I separate the x components, it looks like they cancel. But the y components, right, this would be, let's say, the one on the right, well, the one on the left is also going down. To me, it looks like this one, this arrow here is a little bit longer. So I figured there was a little net force up. And when you look at these arrows, it looks like this one here, right, is a little bit further or a little bit longer. So therefore, I was guessing that the x component of this one would be slightly longer than this one, and so that's why I said it's going up, it's a little over, and so the net force would be up and to the left. You could definitely argue that these two arrows look identical in length, therefore their x components would be equal and they cancel out. And if you thought that these two cancel out, then you would be just left with a net force that was going up. Okay, and number 4, be careful here, and it says down here, right, that the x and the y-axis are different compared to our lab. In our lab, we graphed force and acceleration, and the slope was the mass. Well, and from that we got F equals ma. Well, if all of a sudden we have acceleration and force, right, then we're going to have an equation that looks like acceleration equals the slope over the force, right? We got to figure out what goes in the slope. Well, if we rearrange this equation, you get A equals, right, F over m. That's like saying A equals 1 over m times F. So 1 over m is the slope, which means if I have a mass of 2m, right, that means I'm really need to graph 1 over 2m, which means I need a slope of a half. And that's why my triangles that represent 2m, right, have this slope here of 1/2. So vice versa, right, for part B, now I'm 1/1/2 for the slope. So if I multiply this side by 2 and this side by 2, I get a slope of 2, and that's why for the squares that represent my 0.5 mass, I actually have a slope of 2. So you've got to be really careful. You probably have your graphs that look the same as these, but you probably have these here as triangles and these here as squares. You have them switched. So be really careful on those, that because, if I can erase some of this stuff, right, because the axis is switched between acceleration and force, now this slope is representing the 1 over the mass, not the actual mass. Okay, for page number 2, right? Okay, number 5, a steady force is applied to a 2 kilogram mass causing it to accelerate at 4. The same force was then applied to a 4 kilogram mass, so we know that our mass went from 2 to 4, so essentially we have twice the mass. Using the relationships, find the acceleration of the 4 kilogram mass. So, as I showed here in this part of my explanation, right, I rearranged it so A equals F over M. I can then get this relationship, I can get this relationship that A is inversely proportional to mass. So if it's inversely proportional, as one increases, the other one will decrease. And so because our mass doubled, that means our acceleration is going to decrease or become 1/2 of what it was before, right? And 1/2 of 4 is 2. For number 6, it's just still using those same relationships. So if we have, right, F equals ma, we know that force is proportional to mass, right? Force is proportional to acceleration, and acceleration is inversely proportional to mass. So now we look, okay, well, if the force is doubled, right, we want to know what will the acceleration be. So if the force is doubled, then the acceleration is doubled because they're proportional. So our 10 went to 20. For part B, the mass is doubled. Well, if our mass is doubled because it's an inverse relationship, if our mass gets bigger, then the acceleration gets smaller. So double the mass, half the acceleration. So if the acceleration was 10, we cut it in half, right? So 1/2 the acceleration was here, and this was twice the acceleration. So part C, the force is doubled, and the mass is doubled, so that one's a little bit harder, so we've got to do both. If the force is doubled, then we know the acceleration would be doubled, right? So all of a sudden we'd be saying, okay, well, we're going to have twice the acceleration. But the mass is doubled, and if the mass is doubled, then the acceleration, because it's an inverse relationship, the acceleration would be cut in half. So then we'd say, well, wait, because of that relationship, it would be half the acceleration. Well, if one causes the acceleration to double and the other causes the acceleration to cut in half, the net result is no change at all. The acceleration stays the same at 10. Part D, a force is doubled and the mass is halved. So same idea. If the force is doubled, because it's proportional to acceleration, we know that that would be double the acceleration. And if the mass is halved, using that relationship, right, if we're 1/2 the mass, right, that would cancel. That would leave us twice the acceleration. So that means that that will also double the acceleration, which means we have 4 times the acceleration, or 40 meters per second. And you're going to have to be able to use those relationships in the multiple choice questions and part of the free response questions. So let's see, our last one for this video, number 7, we're trying to do force diagrams. If we hold the object at rest, we know that the net forces have to be 0, so our normal force and our weight are identical. For part B, if your hand is moving up before the rock leaves the hand, I'm assuming in mind that it was accelerating up. And so if the rock is accelerating up, then the force lifting up on it must be greater than the force pulling it down, so the normal force has to be bigger. For part C, right, 1/10 of a second after the rock leaves your hand. So after it leaves your hand, it's in free fall, essentially. So you know that the weight is pulling down on it. Because it's in air, right, that was double underlined, that means there's going to be some air resistance. It's always in the opposite direction it's moving. So if the rock is moving up, then the air resistance is going to be down. And because there's nothing else that's touching the rock, there's no forces up. So there's no forces here, right, because there's nothing that's pushing it up at that point. So last one, part D, after the rock has reached its highest point and is now falling down, at its very highest point, what's its velocity? It's 0. If it's not moving, that means, right, that the air resistance is 0. That's supposed to say air there. So that's why, I guess it says it's reached its highest point and it's now falling down. So I guess it's really how you interpret it. If you interpret it at the very, very top part, you would say the air resistance is 0. I guess I thought, well, it's now falling down, so I put some air resistance up instead of down. It depends on how you interpret it. Obviously, when I started explaining it, I was thinking, well, if it's at its highest point, it's not moving, and therefore the only force would be the weight. Just depends on how you want to go. Okay, hopefully that helps, and I will have the other videos for each question.